Okay, today I'm going to finish this up. I'm going to finish this up sigma s. We started Monday, and I'm going to finish this. But as you notice, probability models, you can change from one to the other, but some model is tricky, and getting slightly more difficult. Even two parameter, the resistance and the loading is going to get complicated. But still next week, Monday through Friday, I'm going to cover. Monday, Wednesday next week, I'm still going to cover two parameter situation, which means both are random situations. So you are slightly exposed for that situation also. But I'm going to cover some, then you know the direction what to do. Then we are going to go into the multidimensional general situation, starting with the first order reliability method. Then you will wake up from that moment for a month, because you're gonna program as a group to solve the problem. Toward the second week of November, I want you to think about the term, sort of the term project, then of course multi-parameter situations. Then Monday, I'm going to, maybe toward this tomorrow, Friday, I'm not gonna be here, so at least by Monday, you will have two sets of the file on the so-called most preferable point, and the Professor Du's chapters, he didn't publish yet, but draft is what you're gonna get it. Is that a copy? No. See? Oh, okay. Okay, so that's the plan. Then you will spend maybe a week to generate the project. Then I want to review your project proposal. Then you will be busy for the rest of the semester. So here we have done for deterministic actual stress situations and random yield stress for the rectangular type of the probability distribution model. So today I'm going to do the, this is, of course, this is a deterministic. And the yield stress is exponential. Monday I mentioned to you what probability model I will cover, and I said you do the log normal probability model for the yield stress. How many tried it? It's up to you whether you'll try or not, but I said try it. so don't regret later that I haven't tried it. So so this is only the random. So first thing you have to look at is that yield, okay? Yield stress is random. This is 0. If this is below, equal to 0, or you can just you can include 0 down here. So a exponential minus a sigma y, sigma you can include 0. Okay. And next is, of course, you have to do the cumulative probability distribution model, and sigma y. Sigma y is given value, okay? So this is a probability. And when I do the lecture today, I discovered some error when I prepare the notes. I'll point out where to make corrections, okay? It's a probability such that, the probability such that the random yield stress here is less than equal to sigma y. So for the general definition is concerned, I wrote like this. General definition minus infinity to upper limit. In this case, for exponential distribution model, in this case is a density model, this minus infinity you have to replace 2, 0. Some corrections. Mathematically, it's good. For this case, lower limit has to be the 0 to upper limit is sigma y. That's a given specific the value. Then if you do that, then you integrate, then 1 minus exp in this case, you know, I just mathematically the yield probability model, we use exponential model. Can you think of, in reality, what kind of the material as a yield stress, what kind of a material could have exponential kind of the probability model? As we deal here is actual stress and the yield stress, yield, which we are talking about probability density model is something like this. So this is yield stress. This is like, can you think of something? I suddenly just feel, rather than just to pick up the exponential model. So when you talk about the yield stress, that's a part of the resistance of the material. As yield stress is getting larger, then it's lower. What kind of material? Who cares? Smile. Think about it. Kiwan. Such a model, do you think is a good model to pick out, use as to build whatever the system? I wouldn't like it. Degrading, yield is really degrading. So what result do you expect in terms of the reliability? I expect not the very good in terms of the reliability of to build the system. Like a brittle material like a titanium. Titanium materials belong to the brittle material family. Yield stress could be very high. Then it just goes to boom, down to zero. But in the naval application, we are using quite a bit. Not really US heavily, but Russian submarines are titanium. Russian submarines are much larger than US submarine. And it has the pressure hull inside the outer the hull, which is not the pressure hull, but they have titanium. Titanium is really brittle material, but there are lots of other merits that the Russians are using it. It's very difficult to weld. They have to do the welding in the water. To avoid the lots of difficulties, I forgot all that point of difficulties. And this material, as a yield, personally, I expect I wouldn't use it. But US submarines is concerned, this is all unclassified, unlimited distributions, like HY100. HY100 is a really high yield type of the material. That's what they are using it. So like yield stress is 100 kpsi. 100, that's what I meant. 100 kp. Kilo psi, you can convert into megapascal. The carbon steel, for the construction steel, which is a general carbon steel, that construction grade steel is 36 kpsi, is typical their yield for the constructing the buildings and all that. But for the submarine, very high. But this is a ductile material. So ductile material, so elongation, as you increase the stresses in the tension bar test, it increases, elongation increases, and pretty good ductile in nature. But titanium, no. So so that's what you expect here. But you can integrate this, then you have this, then as usual, as we have done last week, then I can multiply the step function. So or you can say sigma y is greater or equal to 0. So this u means is step function. This way you did, or we did. And so now this is model defined probability model, density, and the cumulative distribution function. Then of course we have done this model last week, and you can get the expected value of this. Expected value, you know the definitions, integration of that multiply the probability density function, and the variance is equal to 1 over a squared, and this means the square root of variance sigma y, which is called standard deviation, is equal to 1 over a, right? Which is telling us that coefficient of variation, which is e to the, just to rewrite to make sure, square root of variance sigma y standard deviation. What's the value? 1. Is it good? Spread is huge, right? 1. So at this point, you can tell not a good material to use it for designing your system, regardless, because the spread of the yield is just flat. So this is COV, coefficient variation, superbly high, then I don't recommend. Somebody might have a reason to use it, but I wouldn't recommend it to use this at all. But regardless, we're going to finish this up. Then question is, what's the reliability? And if you know, you can compute the PF, which is 1 minus R. So reliability is concerned the probability sigma S is less than sigma Y. I want to drop again equal sign to make it consistent, okay? The probability failure, as I talk based on Kiwon's questions and comments, failure plane, I want to include in probability of the failure side. For the reliability, we're going to exclude that plane, which surface, which means take away the equal sign. So reliability, back to always definition for computation. So this is equal to, rewrite once again, just the same thing, but to the convenient expression, sigma y is greater then sigma s. Then now this is equal to 1 minus PF, which is a probability such that sigma y is less than equal to sigma s. So this guy is probability of failure. Always complement each other. Okay, so which means R is equal to 1 minus, that's F, and this is yield sigma s. Sigma s is given value. So which you can, we have the cumulative distribution function is right here. Replace, there is a sigma s, so replace, we're going to replace sigma y to sigma s. Okay, so to do that, you have 1 minus exp minus a sigma s u s, okay, over here, sigma, oops, I don't have to write. So this is a step function. So by doing this, 1 cancels up, then R, P, oh, this is R, right? R is equal to, finally, exp minus a. Looks like R, a sigma s either way, whether you introduce a step function or say greater than 0 is the same thing. There's no differences. So this is final expression. Then or you can write this guy as exp. A is, we know this relationship. A is 1 over mean of sigma y. So you can re-express this guy as minus sigma s e to the sigma y. So this is for the reliability. We can define that. Then what you can do here is you can express, you can use N1. So this is R. So you can introduce N1. N1 is e to the mean of the yield divided by, in this case, is actual stress, which is deterministic, then you can put that in. Then for given or required for design, R, which is equal to R, we said specific reliability level for design, then you can just rewrite this expression just to take a natural log. You have N1 is equal to minus 1 over natural log R, or you can just rewrite, put the minus sign in there, then you can write as same thing, 1 over R. Then you will see when you look, equation looks okay, but coefficient of variation, in this case for yield, is 1. Uncertainty is terribly bad for material. Then you expect the safety factor goes zoom up, you know, for almost any reliability. So if you compute, let's say 90% the reliability, if you compute N1 is 9.49, for 99% reliability, this comes as a 99.45. Stupid dumb, isn't it? So that's why coefficient of variation is always good to check. Coefficient of variation is normalized one, and it shows the spread of a probability model. So so you can really tell this is not the model. Okay. But anyway, it's a probability model. Sometimes you are tasting good meal, but sometimes when you are someplace where you can access any good meals, anything, sometimes you have to taste a bad meal. So this is one of those. Even if material is not available, you have to be careful. You can't just pick and build anything you can access. Okay, so this is one of the cases. Exponential distribution. But you know, most of the materials, many materials, I can say, follow the normal distribution. It uses heavily, you know, people use normal distribution model heavily. It has a reason. Last of category of material follow normal distribution very well. So another situation we're gonna looking into, not today maybe, when it has a correlation between or among the random variable, it's a terrifying. It's a bad. In this case, we use actual loading and strengths. If it's correlated each other, if there is a correlation, gosh, you just can't analyze, because unless you really know the correlation between loading and the strengths, don't know what to do. One of the category in the problem is like a fluid structure. The interactions occurs in there. Then it's very difficult to cast into. It's reasonable to cast into the formulation using the correlation functions and all that. But the question is prediction, simulation. Then in the process of prediction and simulation, what level of the correlation are you going to assign? Difficult. So the Lord, the God, He's always reasonable, and such that loading and the strength usually correlation, even if there is certain correlation, very low. Mostly you can neglect it to get the reasonable prediction. I didn't deny it's uncorrelated, but that's the way we can compute that, okay? Okay, we're gonna do a couple more model. Rayleigh distribution is pretty well used as a good probability model for structure reliability computation. Whether it's a dynamic situation or static situation, is pretty well used. So, which is case number 3, and basic model is like this. Of course, it has a skewness in the model. Usually start from the 0. So this or this doesn't make any difference. And page 8-9, 8-7, there's a mistake there. I said actual stress is, that's wrong, right? Clearly wrong. So this is not actual, which is yield stress is correct. Same routine, same procedure. This is the probabilistic model, which means you can define the probability density function of yield stress. Sigma S is what? What's the sigma S? Deterministic, right? In this case. So we cover all that. Then last combination we're going to do next week is both are the random situation. Then that's about all. So 0 for sigma y is less than 0. And the sigma y b square exponential minus sigma y square. What the b here, what the b does it for the curve? B is the only parameter in Rayleigh distribution. This is probability density function, you can say that. So B is the parameter which affect the skewness of the probability model, definitely. And of course, the sigma y is of course affecting the heights and all that. B, as you look back the Rayleigh distribution, in the section I covered the probability, probability model, then there is a Rayleigh distribution, so you can really see the sensitivity of the curve based on the parameter, the B here. And this is the case, sigma y is that. And the probability distribution function for the strengths is equal to the probability such that y is less than equal to sigma y, and which is integration minus infinity to, if you look at my note, I said sigma f y sigma d sigma. What's wrong here? Chui, what's wrong? Minus infinity in this case should be start from 0. And what about this guy? Yeah, we are dealing with this guy, right? So this guy should be some correction, because all the notes you are having is really, I sit down and type up using this book, that book, and it's like that. And so if you so we have Rayleigh probability density function up here. If you do that, you have 1 minus exponential function sigma y squared That's about all you're going to have. Then now you have a probability density function, you have a probability distribution function for the yield. So now you are ready to write the reliability, structural reliability, or the probability of the failure. That's the end of it. So when you design the system, structural system, then the first design parameter you have to consider is what's the structural reliability wants. If you want to have 99.99% the reliability, you are wrong. Because the structural reliability you can replace. To replace, cost is terribly high. For the equipments, you know, when electric switch is bad, you can replace it with a few dollars. But for structural collapse, you have to really rebuild the whole system. So usually very, very expensive. So at least, as I briefly mentioned at the beginning of the class, is 10 to the minus 4th power to 10 to the minus 6th power, which means in the probability margin, I should say safety margin, That's what we learned, the P and R, or S and R. Loading and strength. That generates the surface for probability density function. Then you know the safety margin is equal to R minus P. You can visualize yourself, right? Can you visualize yourself? That's a safety margin. The safety margin generates the limit state function. Jinggyun, you pay attention? That generates so-called G function. The G function is the plane which cuts the probability density function based on the P and R. And G function has to be less than or equal to 0, which is really low, very low end of the whole volume. That cutting plane, G function, limit state function, then that edge to compute the probability of failure, you have to be careful because you're computing a very small number. So sometimes not quite integrable, or you can integrate, but if you want to just use regular methodology to integrate, you will have a tough time. So that's why first order integration not working, getting into second order the approach to get more precise definition of the surface to get the integrations. But here, first order, the integration I feel should be sufficient. Most of the system I feel looks like it's sufficient, so we'll concentrate doing first order the reliability method to compute the probability of the failure, then should be able to design the product or the system. That's what we want to do. Okay. Okay. So here is one last definition to complete is R. R is again, wrote this 10 times over 10 times. Sigma S is less than sigma Y, which is equal to 1 minus probability, such that the sigma Y is less than equal to sigma S is equal to 1 minus F Y sigma S, okay? So if you compute that, you have exponential function minus sigma S squared to B squared. Zero. Or you can use a step function, that's the same thing. Then you can compute parameter as usual, expected value or mean value of yield stress. This happened to be 1 point, there was a mistake in my note, minus infinity to infinity sigma minus e to the sigma y square. Oh, before do that, what I want to do, the way I wrote there in page 8-8 is sigma f. I wrote s sigma d sigma. What's wrong here? What's wrong here? 성태, what's wrong here? This guy is wrong. The S actual stress is deterministic in our case. So this should be y. Then what's wrong here? What about the lower limit? Should be 0. Then if you do that, then you can compute this is 1.25b. So b has direct connection to the mean value. So mean value is equal to 1.25b. b is equal to mean value sigma y over 1.25. We use mu as mean value. And also the variance I keep writing the VAR, variance, standard deviation square. You have 0.43 b squared. This is equal to 0.8. Then you can express this R. You can express this R using N1. You can have EXP one to 5. I can still write this as sigma s is greater than equal to 0 because the definition of N1 is equal to sigma y over the can I write this? Yeah, because this is a deterministic. What am I doing? Sigma s N1 is a function. Okay. So in this case, it's really reasonable when you compute the R and N1. It's reasonable because 90% you got 2.73. 99% you got 8.81. 99.99 you can compute something pretty high. Okay. The last model I am going to do, not today, is very straightforward for normal distribution for sigma y. Sigma y is a normal distribution. What's the process for handling the normal distribution? Well, first you have to write down the probability density function. You know that. Then you have to integrate to get the cumulative distribution function. Then, because it's a normal distribution function, you can cast into what form? The standard normal distribution. Shift the mean to right at the 0, right? Visualize it. 형태, right? Look at me, right? 중간, look at me, you too. Set the mean 0 means transfer back to mean is equal to 0 and sigma is equal to 1. Then everything is all beautiful. You are not tangling up, you know. So then you can just look up the table. You don't have to get into MATLAB just to calculate the reliability right there. But you have to compute so-called the reliability index. You all forgot about reliability index. It's coming back tomorrow. You forgot reliability index. Maybe not, because you are using all the time, maybe some of you. Okay, that's what we're gonna do. I'll stop right here. And Monday, we're gonna continue this for maybe 5 minutes. Then we are going into the both random situation. Then after that we are gonna go right into the multidimensional. Okay? All right, so I'll see you, not this Friday, so Monday I'll see you. So you have some good time to prepare the review, the stuff. It's open book. That open book doesn't mean to me make the problem so difficult just to give a totally different things and let everybody fail. That instructor's stupid, isn't it? Okay, see you next Monday.